Today we're diving deep into a paper titled Local Policies Enable Zero-Shot Long Horizon Manipulation. This research tackles a significant challenge in robotics, enabling robots to perform complex, multi-step tasks without extensive, task-specific training. What are the key limitations of existing approaches that this paper addresses?
Current robotic manipulation methods often struggle with generalization. They frequently require massive data sets, often collected manually, and even then generalization is limited, often failing when object poses or scene configurations deviate slightly from the training data. Sim-to-real transfer has shown promise, but accurately simulating complex contact dynamics and generating realistic task distributions remain major hurdles. This paper aims to overcome these limitations by introducing a novel approach based on local policies.
Let's unpack local policies. How do they differ from traditional approaches, and what advantages do they offer?
Local policies focus on a localized region around the target object, making them invariant to the absolute pose of the robot and object, the order of skill execution, and the global scene configuration. This inherent locality significantly reduces the complexity of the problem and improves generalization. Instead of learning a single monolithic policy for the entire task, the approach decomposes the task into smaller, more manageable subtasks, each controlled by a local policy.
The paper mentions the integration of foundation models. How do these models contribute to the overall system's capabilities?
Foundation models, specifically visual language models, VLMs, are crucial for task decomposition and understanding. Given a text prompt describing the task, the VLM breaks it down into a sequence of sub-goals. These sub-goals are then used to guide the motion planning and execution of the local policies. This hierarchical approach allows the system to handle long-horizon tasks effectively.
The paper highlights a two-phase training approach. Can you elaborate on this process?
First, they train numerous state-based expert policies using reinforcement learning, RL, in simulation, focusing on specific manipulation skills like picking, placing, and handling articulated objects. These policies are trained on a massive dataset of diverse objects and scene configurations. Second, these expert policies are distilled into generalist visuomotor policies using de-agger, dataset aggregation, a form of imitation learning, to improve their robustness and ability to transfer to the real world.
The choice of observation and action spaces is critical for sim-to-real transfer. What design choices were made in this research and why?
The observation space incorporates privileged information, such as object key points and reward components, to accelerate learning and improve performance. The actions are delta pose targets for a task space impedance controller, allowing for precise control. Crucially, all observations are localized to the interaction region, ensuring the policy's invariance to global scene changes. Depth maps from a wrist-mounted camera are used, which are inherently local and transfer well from simulation to reality.
The paper presents impressive results on both simulated and real-world benchmarks. Can you summarize the key findings and comparisons to other state-of-the-art methods?
In simulation, the method outperformed or matched state-of-the-art methods on RoboSuite benchmark tasks, achieving a 97% success rate. In real-world experiments across 50 long horizon manipulation tasks, it achieved a 76% success rate, significantly outperforming methods like Sayhaken, OpenVLA, LLM Trades Gen, and VoxPoser. This demonstrates the effectiveness of the local policy approach and the robustness of the sim-to-real transfer.
What were some of the key challenges encountered during the real-world evaluation, and how were they addressed?
Challenges included vision failures, incorrect object detection, imperfect motion planning leading to collisions, and local policies failing due to suboptimal initial poses. The paper suggests future work could address these issues through techniques like training value functions per module, incorporating closed-loop replanning, and online adaptation of the modules.
The paper mentions limitations related to depth sensing and the simulation of complex contacts. How significant are these limitations, and what potential solutions are suggested?
The reliance on depth sensing limits the system's ability to handle shiny, reflective, or transparent objects. The authors suggest exploring methods that learn depth from RGB images as a potential solution. The limitation of simulating complex contacts restricts the applicability to tasks with significant state changes. However, the local policy framework is adaptable to real-world data, offering a path to overcome this limitation.
Looking ahead, what are the most promising avenues for future research based on this work?
Future work could focus on improving robustness by addressing cascading errors through techniques mentioned earlier. Expanding the skill library to encompass a wider range of manipulation tasks is another important direction. Finally, exploring the integration of other sensor modalities beyond depth, such as tactile sensing, could further enhance the system's capabilities and adaptability.
The paper's focus on local policies offers a compelling approach to improving the generalization capabilities of robotic manipulation systems. The combination of local policies with foundation models for task planning and execution seems particularly promising. What are the broader implications of this research for the field of robotics?
This research significantly advances the field by demonstrating the feasibility of zero-shot, long-horizon manipulation. The approach's scalability and robustness suggest a potential paradigm shift in how we train and deploy robotic manipulation systems. It opens doors to more general-purpose robots capable of adapting to a wider range of tasks and environments with minimal human intervention. The modular design also allows for easy integration of new skills and improvements in individual components.
The modularity of the system is a key strength, allowing for independent improvements in different components. This makes the system more maintainable and adaptable to future advancements in various subfields. How does this modularity contribute to the long-term viability and scalability of the approach?
The modularity is crucial for long-term viability. As better VLMs, motion planners, or RL algorithms are developed, they can be seamlessly integrated into the existing framework without requiring a complete system redesign. This allows for continuous improvement and adaptation to new technologies, ensuring the system remains state-of-the-art for a longer period. The scalability comes from the ability to train and add new local policies independently, expanding the system's capabilities without needing to retrain the entire system.
The success of this approach hinges on the quality of the foundation models used. How sensitive is the system's performance to the choice of VLM and motion planner? Are there specific characteristics of these models that are particularly important for optimal performance?
While the paper uses specific models, GPT-4 and Neural MP, the framework is designed to be agnostic to the specific choices. However, the performance is certainly influenced by the capabilities of these models. For the VLM, strong spatial reasoning and the ability to accurately interpret and decompose complex tasks are crucial. For the motion planner, speed, robustness, and the ability to handle complex environments and obstacles are key. Future research could explore the impact of different model choices and optimize the system for specific model characteristics.
This discussion has been insightful. Thank you for explaining the intricacies of this research. The focus on local policies, combined with the power of foundation models, presents a significant advancement in robotic manipulation. The modularity and scalability of the approach are particularly compelling, suggesting a promising future for more general purpose and adaptable robots. Thank you.